Welcome to today's paper reading. Today's paper is titled, M2 Depth, Self-supervised Two-Frame Multi-Camera Metric Depth Estimation. This paper was published on AR14 by Yingshuang Zhou and colleagues from Tsinghua University and Megvi Technology. The M2 Depth Network is a novel self-supervised system designed for two-frame multi-camera metric depth estimation. It processes temporally adjacent images from multiple cameras to produce high-quality surrounding depth. Key innovations include the construction of cost volumes in both spatial and temporal domains, a spatial-temporal fusion module, and the integration of SAM features to enhance depth edge detection. M2 Depth has demonstrated state-of-the-art performance on new scenes and DDD benchmarks. M2 Depth is a novel self-supervised network designed for two-frame multi-camera metric depth estimation. The key insight behind M2 Depth is the integration of spatial-temporal information to enhance depth accuracy. This is achieved through the construction of 3D cost volumes and the use of a spatial-temporal fusion (STF) module. Additionally, M2 Depth innovates by integrating features from the segment anything model (SAM) through a multi-grain feature fusion (MFF) module, which significantly improves depth quality. These innovations have led to state-of-the-art performance in multiple surrounding depth estimation benchmarks. Figure 1 presents a comparison of point clouds generated from depth predictions on the DDD dataset. The figure demonstrates that our M2 Depth method produces more consistent and accurate point clouds compared to surround depth. The point clouds are visualized using the surrounding depth from a single frame, with challenging areas that span multiple cameras highlighted by blue boxes. This comparison underscores the superior performance of M2 Depth in handling complex scenarios involving multiple camera views. In multi-frame depth estimation, methods like monorec and many-depth use adjacent frames to enhance depth quality, which significantly improves practical applications. For multi-camera depth estimation, techniques such as FSM and surround depth focus on recovering the surrounding 3D environment in autonomous driving scenarios. Additionally, the segment anything model (SAM) has been applied to various tasks including depth estimation, leveraging its fine-grained semantic segmentation capabilities. Figure 2 provides an overview of the M2 Depth system. The system begins by estimating the pose of the front camera, point T-1, using images from multiple cameras in 2 frames. This pose estimation is crucial for inferring the poses of all other cameras. The multi-grain feature fusion (MFF) module then aggregates internal features from the SAM encoder to enhance feature expression. This module is essential for improving the depth prior estimation. The depth prior and constraints across multiple cameras are used to construct 3D cost volumes within the temporal spatial domain. These volumes are then processed by the spatial-temporal fusion (STF) module to improve accuracy and consistency. Finally, the depth decoder uses these processed volumes to produce the surrounding depth. M2 Depth addresses the surrounding depth estimation task in autonomous driving using multiple cameras mounted on ego vehicles. The problem is formulated with C cameras having known intrinsics and extrinsics, aiming to produce scale-aware surrounding depth. The network architecture involves pose estimation from the front view, monocular prior estimation, and the construction of spatial-temporal cost volumes. Experimental results demonstrate significant improvements in depth estimation metrics compared to existing methods, achieving competitive performance on the new scenes dataset, while maintaining a balance between memory usage and computational efficiency. Figure 3 illustrates the structure of the multi-grain feature fusion (MFF) module, which is crucial for depth prior estimation. The MFF module processes internal features (CC) C=1 and SAM features (SC) C=1. It employs a fadden block to create a weight map WC that captures complementary information between CC C=1 and SC C=1. This weight map is then utilized in the fusion block to generate the fused feature MC C=1. This fusion process enhances the understanding of the 3D environment by integrating fine-grained semantic information from SAM features with depth cues from internal features. Figure 4 provides an overview of the volume construction and the spatial-temporal fusion (STF) module. The process begins with the reference image feature FCT and its temporal spatial adjacent features. These adjacent features are warped to the reference view, resulting in the formation of initial volumes VCT, TP in the spatial domain and VCT, SP in the temporal domain. The STF module then comes into play, fusing these initial volumes by computing the correlation between FCT, TP. This computation yields weight maps WCT, TP, which serve as fusion weights to guide the final volume fusion. The final spatial-temporal volume VCT is thus created, integrating the information from both spatial and temporal domains, enhancing the depth estimation process. Figure 5 presents a qualitative comparison of the predicted surrounding depth on the DDD dataset. The top row shows the input surrounding images, while the subsequent rows display the visualized depth maps and depth errors of surround depth and M2 depth. The depth maps are visualized within a range of 0 to 50 meters. Our method M2 depth is shown to produce more accurate depth with reduced error and sharper depth edges across multiple cameras. This demonstrates the superior performance of M2 depth in accurately predicting surrounding depth in challenging scenarios. Figure 6 presents the visualization results of different features within the M2 depth model, specifically on the DDD dataset. The internal feature is derived from the internal image encoder, providing geometric distance information. The SAM feature originates from the frozen SAM encoder, which contains semantic instance information. The fused feature, produced by the multi-grain feature fusion (MFF) module, combines these two types of features in latent space, offering a comprehensive understanding of the surrounding environment. This visualization helps illustrate how the integration of internal and SAM features enhances the model's feature expressiveness and overall performance. Table 1 presents the quantitative results of M2 depth and other methods on the DDD and new scenes datasets. The metrics include absolute relative error (ABS), REL, squared relative error, square REL, root mean squared error, RMSE, RMSE log, and accuracy thresholds, delta less than 1.25, delta 1.25/2, delta 1.25/3. M2 depth shows competitive performance, particularly in reducing ABS, REL and RMSE on both datasets. The table highlights the number of frames used in training and testing phases and distinguishes between different implementations of the same method, denoted by asterisk. Bold figures indicate the best performance, and underlined figures indicate the second best. Table 2 presents the per-camera evaluation results on the DDD dataset, highlighting the performance of various methods across different camera views. The table shows that our method, M2 depth, achieves superior overall performance compared to existing works such as FSM, surround depth, SD, and our 3D3 star. Notably, our 3D3 asterisk results are obtained using the official code with the same frame setting as ours. The evaluation metrics include ABS, REL, square REL, RMSE, RMSE log, and delta, which are reported for each camera view. Additionally, the table provides insights into the memory and computation efficiency of each method, demonstrating that M2 depth strikes a good balance between overall performance and computational efficiency. This balance is crucial for practical applications where resource constraints are a concern. Table 3 presents the quantitative results of an ablation study conducted on the DDD dataset, focusing on the M2 depth method. The table highlights the impact of different components such as monoprior, MP, spatial volume, S.volume, temporal volume, T.volume, and the spatial-temporal fusion, STF, module on depth quality metrics. The results indicate that the integration of spatial-temporal cost volumes significantly enhances depth accuracy compared to using monoprior depth alone. Additionally, the STF module further improves the performance across various metrics, demonstrating its effectiveness in increasing the capabilities of M2 depth. Table 4 presents the results of ablation studies conducted on the DDD dataset, focusing on the effects of ledge, depth edge loss, MFF, multi-grain feature fusion module, and depth decoding with SAM features. The data indicates that ledge contributes to improvements in absolute relative error, ABS, REL, and squared relative error, square REL. The MFF module is shown to enhance the fusion of multigrain features, while depth decoding utilizing SAM features results in the best overall performance for the M2 depth model. These findings underscore the importance of each component in the model's architecture for achieving optimal depth estimation accuracy. The depth decoder in this study involves transforming the spatial-temporal volume, VC, using 3 DCNNs, calculating the spatial-temporal depth, DC, and obtaining the final depth, DC, by integrating the upsampling mask, MC. For adaptive depth sampling, the method uses the mono-depth estimation result as prior information to conduct adaptive sampling, significantly reducing computational complexity. The structure from motion loss is calculated to enhance the accuracy of depth and pose estimation by leveraging information from neighboring cameras and extrinsics. Figure 7 provides an overview of the depth decoder process. It begins with the spatial-temporal volume, VC_T, C_C equals 1 and the SAM feature, SC_T, C_C equals 1 as inputs. The spatial-temporal depth, DC_T, SD, C_C equals 1 is initially computed and then upsampled using the mask, MC_up, C_C equals 1. This process results in the final depth, DC_T, C_C equals 1, which is calculated from the SAM feature, SC_T, C_C equals 1. This method ensures efficient and accurate depth estimation by leveraging both spatial-temporal information and SAM features. Figure 8 demonstrates the concept of adaptive depth sampling, where the depth range for each pixel is determined based on its initial depth and a scaling factor. Specifically, for pixels farther away, the depth range increases, while for closer pixels, the range decreases. This adaptive approach aligns better with the actual depth distribution of scenes, thereby enhancing depth estimation quality. Figure 9 presents the visualization of depth results produced on the DDD dataset. The integration of SAM features results in a significant enhancement in both the depth prior and the final depth, particularly noticeable at the edges of instances. This improvement is evident in the increased consistency within instances and the better discrimination between different instances for both depths. Figure 10 presents a qualitative comparison of predicted surrounding depth on the new scenes dataset. It highlights the depth maps generated by our method in contrast to those from the state-of-the-art surround depth approach. The key observation is that our method yields significantly sharper and more accurate depth predictions, especially in capturing fine details. This improvement is crucial for applications requiring precise depth information, such as autonomous driving and robotics. Figure 11 presents a qualitative comparison of the surrounding depth predictions on the DDD dataset. The comparison is between the depth maps generated by M2 depth and those from the state-of-the-art surround depth method. The key observation is that M2 depth produces significantly sharper and more accurate depth predictions, especially in the fine details of the scene. This highlights the robustness and effectiveness of M2 depth in diverse scenes, particularly at object edges where the method excels in producing clear depth boundaries. Table 5 provides a detailed computation analysis of each module in the system, including the pose branch, image encoder, SAM encoder, prior decoder, volume construct and fusion, and depth decoder. The experiments were conducted on a V100 GPU. Key findings include the significant memory usage and time consumption of the volume construct and fusion module, which accounts for 33.06% of the total memory and 75.39% of the total time. The table also highlights the memory and time percentages for each module, indicating the relative computational load of each component. Table 6 presents an ablation study on the design of the pose estimation module, comparing different methods. The study shows that the method utilizing the front view camera (F-cam) to estimate the front view pose and subsequently infer the ego pose is more effective for the depth estimation network. This method, which estimates the pose of the front view camera P0TT-1 and then derives the ego pose point T-1, outperforms the baseline method that concatenates surrounding views to directly predict the ego pose, contact camera C-cam. The results indicate that the F-cam method is well suited for the depth estimation network, demonstrating its effectiveness. Bold figures in the table indicate the best performance, while underlined figures indicate the second best. Table 7 presents a comparison of different designs for the Feature Fusion module. The MFF, Multi-Feature Fusion, module is trained as described in the main paper, while the VFF, Variant Feature Fusion, module is trained to fuse internal features and SAM features through direct addition. The experimental results show that our design effectively integrates features of various granularities, significantly improving the quality of depth estimation. Bold figures indicate the best performance, and underlined figures indicate the second best. Table 8 presents a comparison of depth decoder designs, specifically focusing on SAM Refine and Vanilla Refine. SAM Refine is trained as described in the main paper, while Vanilla Refine utilizes the context feature from FBN. Both networks are evaluated on the DDD dataset, demonstrating that SAM Refine effectively improves depth quality. The table highlights the best and second best results with bold and underlined figures, respectively. Table 9 presents a comparison of different depth sample designs, specifically adaptive sample, A, sample, vanilla sample, V, sample, and fixed sample, F, sample, each trained with 16 samples. The evaluation on the DDD dataset demonstrates that the adaptive method, A, sample, consistently yields superior results compared to the other two methods. This table highlights the effectiveness of adaptive sampling techniques in enhancing depth quality, as indicated by the bold and underlined figures representing the best and second best performances, respectively. Table 10 presents an ablation study on the number of bins used to train the network. The study aims to compare the influence of varying the number of bins on the network's performance. The results indicate that increasing the number of bins does not significantly enhance the quality of depth estimation. This finding suggests that the use of adaptive depth samples effectively contributes to improving computational efficiency without the need for a larger number of bins. The bold figures in the table represent the best results, while the underlined figures indicate the second best outcomes. Table 11 presents an ablation study on the number of frames used in the experiment. The results show that our method performs highly competitively with only 2 frames. The study indicates that increasing the number of frames does not necessarily enhance depth accuracy. This is because our method is not specifically designed to handle sequence data, so adding more frames does not effectively contribute new information. Notably, using just 2 frames is sufficient to produce commendable results. M2 depth demonstrates consistent robustness and effectiveness across various scenes. Notably, it produces sharper depth predictions, especially at object edges. In comparisons with existing methods, such as surround depth, M2 depth achieves better results, particularly in overlapping views and fine details. The method also shows significant improvements in accuracy and sharpness, with reduced error across multiple camera views. Figure 12 presents a qualitative comparison of the predicted surrounding depth on the DDD dataset. The top row displays the input surrounding images, followed by the visualized depth maps and depth errors of 2 methods, surround depth and M2 depth. The key observation is that M2 depth produces more accurate depth predictions with reduced errors and sharper depth edges across multiple camera views. This comparison highlights the superior performance of M2 depth in handling complex scenes and maintaining depth accuracy. Thank you for watching.